Hello everybody. In this class, I'm going to introduce the dynamic programming, which is an important algorithm for reinforcement learning. Dynamic programming is both a mathematical optimization method and a computer programming method. The method was developed by Richard Bellman in the 1950s. Yes, Richard Bellman is the inventor of the Bellman equation, which is the key of reinforcement learning. So a problem can be solved by dynamic programming if it satisfies two properties. First, it has an optimal substructure, which means that its optimal solution can be decomposed into subproblems. Second, the problem has overlapping subproblems. The subproblems reoccurred many times and the solutions can be cached and reused. Some famous computer science examples include shortest path and Hanoi Tower. And of course, the Markov decision process can satisfy the dynamic programming properties. Let's review the general picture of reinforcement learning algorithms. The R algorithms can be classified based on how they update the value functions. Remember, the Markov decision process can be expanded into a tree structure. The circle is the state, and the black dot is the action. So in this state, we can do different actions and reach different states. Following this expansion rule, we can expand the MDP process into a tree structure. So based on how we update the value function, the horizontal dimension means that we update the state first, while the vertical dimension means we run the policy for several time steps and do backup update of functions of the value function. The dynamic programming is in the extreme upper right corner because they update all states first. So they involve the one-step expected update of all states first. We can use dynamic programming for the Markov decision process because first, the Bellman equation gives a recursive decomposition, and the value function stores and reuses the solutions. Also, the dynamic programming assumes the full knowledge of the MDP. In other words, it requires the knowledge of the model, the environment. So we can use model-based planning. So we need to know how many states we have in the Markov decision process for dynamic programming. Okay, let's see how to calculate the value function using dynamic programming. The first approach is called policy evaluation. The goal is to calculate the state action function, value function v pi, for any policy pi. So we can iteratively calculate the v pi until convergence. The formula is here. So we update our value function v pi using the expectation, calculate the expectation of all the reward from next state for all states belong to the state space. So this equation is equal to the expression e pi is equal to all the actions in this set multiplied by the probability of our policy station. So we calculate all the actions we run all the actions in this state, then based on their probability, and we calculate the transition probability The S prime is next state, reward, and the state action. This is the transition probability between the current action state to next state. And finally, it's multiplied by the reward given by the Markov decision process, and the discount gamma multiplied by our next value function of the next state. So those equations are equal, and we can use the next formula to calculate to update our policy. We keep doing that until V pi converged. Here is an example. This is a small grid world. We have two terminal states. Okay, and we received the -1 reward for each state until the terminal state, and the action leading out of the world remains unchanged. So if you accidentally run out of the state, it will just go back to original state. Okay, so we have 4 actions, left, right, up, down, and the rewards on all transitions are -1. Let's calculate the value function using policy evaluation. Initially, the value function, the values are all 0 in the first iteration, and we are using the random policy. We can calculate using the formula in next slide. We will keep using the random policy, which means the policy, the probability for each action are all equal. Since we have 4 different kind of actions, the probability are 1/4 for each action, right? And the transition probability are equal to 1 by definition in this problem. Okay. So for second iteration, it's the value becomes all -1, right? And the greedy policy is based on the value function, right? Initially, it's also a random policy, so it has equal probability for each action. However, after first iteration, the greedy policy changed because in this state, the best action is to go left, right, and reach the terminal state. In this state, the best policy is to go up. Okay, so now let's try to calculate the value in this iteration. Right? So suppose we know that the probability of random policy. Okay, so one important point is that we keep using the random policy. Although the greedy policy change, but we keep evaluate our value function using random policy. So the policy probability for each action is 1/4. Okay, plus for the transition probability is 1, so we omit it. And for the transition reward, for this reward, this is -1 plus 0, right? The reward are always -1 for each transition, and the state value is 0. So for first one, this is -1 plus 0. For the second movement, it's -1 plus -1. For going left, for going right, for going left, for going left is -1 plus 0. For going right is -1 plus -1. Sorry. So for down is also the same. For going up, it will return to its state and receive the same reward, right? Or remember, we are using the reward in last state. So the new value after update will be minus 1.7 5. It's close to 0.75. We assume the gamma is close to 0, close to 1. We assume the gamma is close to 1. So we can calculate the formula, right? Update our value function using this table. Okay. Let's continue update our value function. Right? For now, again, we are keep using the random policy. Right? We're still using a random policy, so it's 1 for all actions. For going left, right? For going left, we have minus 1 reward plus 0 state value, right? This is for action minus 1. For the action going right, we have minus 1 plus, remember to use the state value of last table, so it's minus 2. For action down, it's minus 1 plus minus 2. For the action up, it's actually minus 1 plus minus 1.7. So the final result will be minus 2.4. Okay, so I hope it's clear. And now let's take a look of the greedy policy. So the greedy policy keep changing in the third iteration, right? So in this state, the best policy is to go left, and in this state, the best policy is to go up. In this state, the best policy there are two optimal policies. There are two optimal actions. One is going up and one is going left, right? So we can keep updating the value function, but after infinite updating, we observe that the optimal policy doesn't change. The optimal policy is the same. So the policy is converged, and also the value function is converged. But in this example, we observe that the greedy policy converged faster than the value function. So how can we improve our policy, which is random policy in the beginning? In other words, how can we learn an optimal policy? Okay, so from last example, we know first we can do the policy evaluation, right? We can calculate and update our value functions. And then we can improve policy by choosing greedy actions. We can find a greedy policy based on the new value function. So we can continue this process iteratively until it converges to some policy as observed in last example. This process is called policy iteration. So here's a picture to describe this process. First, we have initially some random policy. Then we evaluate this function, calculate the new value function, use the current policy until it's converged to certain value, right? And we use the new converged value function to find a greedy policy and use the greedy policy to update. Then again, we follow the new greedy policy, evaluate to converge. Then again, update the policy as our greedy policy. This process is called policy iteration, and we continue this iteration until the value function and the policy, optimal policy are converged, are both converged. So this process is guaranteed to converge to optimal value because each time we at least find a policy, we find a new policy at least as good as the old policy or slightly better. So the process is guaranteed to slightly converge to the true optimal policy and the value function. Okay, now let's see a more interesting example. It's Jack's car rental problem. Suppose there are two locations of Jack's store Jack's company have two locations. Each location has a maximum of 20 cars. The action is that Jack can move up to 5 cars between two locations overnight, and he received $10 for each car rented. The request and the return rate are random. Our probability function follow the Poisson distribution. Remember that Poisson distribution is the discrete normal distribution. So for the first location, the request the lambda is 3 for the average request, and for return is also 3. So it basically has the same rate, the same request and the return rate. For the second location, the average request is equal to 4. The lambda equals 4, and the average returns rate, the lambda equals 2. So intuitively, it means that the second location has more requests than returns. So we better allocate enough car in the second location. So here is the policy and the value function learned in Jack's car rental problem. The vertical axis, the y-axis, means the cars at first location from 0 to 20, and the horizontal axis is means the cars at the second location. So the positive number 5 means that the number of cars need to be moved to second location overnight. And the minus number is the number of locations. The number of cars need to move to first locations overnight. Okay. So intuitively, initially all cars are 0, but if you have more cars at first location, you better move as many cars as you can, which is 5, to the second location. And this policy also converge to this state. So if you have more cars then the second location, has less car, less than maybe looks as 4, then you need to move 1 car to the second location overnight. But if the number of cars at second location increase, then you don't need to move car. Okay. So the value function basically looks like this. The more cars you have, the more value, the higher value. We can try to prove that the policy iteration indeed it will converge to an optimal solution. This is from the David Silver slides. So the policy improvement. First, we consider a deterministic policy A equals to pi. It's a deterministic policy A. So we can improve the policy by acting greedy, right? So we choose the argument max of our state action table, Q table. So this is the greedy policy. So the greedy policy improves the value from any state over one state. So the value policy improve or at least as good as the original policy equals to the policy the value under the deterministic policy, right? So therefore, it's a iterative process. It can keep improving the value function, right? So the new value function, the new iteration will have a better, better value. So this is we can then calculate the Bellman equation, right? It's a recursive process. If the improvements stop, which means we always have equal results, similar results. So in other words, the improvement converged, then the best state action reward will equal to the value of the current policy. Then the Bellman equation or Bellman optimal equation is satisfied. Therefore, we prove that the value policy iteration will converge to the optimal value and optimal policy. So pi is the optimal policy. Now we know that we can use the policy iteration to find the optimal policy, right? This approach is to first iteratively evaluate the value function until convergence, and then use the value function to find the optimal policy. But there's one question. Do we need to iteratively evaluate until the convergence of value function b pi? Can we simply stop after k iterations? Remember in the small grid world that the example achieves optimal policy after just 3 operations. So we don't need to run the iteration to infinity, right? We don't need to wait the convergence of value function. We can maybe stop earlier and the policy function are already optimal. So actually the question is yes. In fact, we can update the policy every iteration. So we can update the value iteration, we can update the value function and immediately update the policy. So this approach is called value iteration. So let's define value iteration. For value iteration, we first update the value function, but in fact, we don't need to calculate the policy function pi because the policy is implicit built using the value function, right? So we can use the new value function to find the optimal policy, right? Because we actually our policy depends on the value function, so we don't need to recalculate the policy function. This approach is called value iteration. Let's take a look at another example. This is a shortest path example. The problem is that to find the shortest path of each grid to the goal, which is labeled as G. So our goal is to find the shortest path to reach this goal. Initially, the value for each state are all zeros, right? So we have a random policy. We have a random policy, and then we update our value function because all rewards are zero, all rewards are -1. So now all the values are -1. Then for this set, we have we can find the optimal policy for those two steps. For this set, the optimal policy is going left, right, and for another one is going up. So the policy actually changed. So it keep having the -1 reward, right? And now for the other grid nearby those two states, they find new policy, new greedy policy. So once they find this policy, they can keep going in this direction, then their value doesn't change, right? So let's keep updating this value function until convergence, and we can successfully find the shortest path for all states. Finally, let's conclude our class with a comparison of policy iteration and value iteration. For policy iteration, we first choose a random policy, right? And then evaluate it to calculate the value function. Then use the calculate until convergence. So evaluate and use the new converged value function to calculate, to update, to improve the policy, and find a new policy one, and keep this process evaluation, improvement, evaluation, improvement until both policy and value are converged. But for value iteration is much easier. We just keep updating our value functions, and the policy are implicitly updated during each calculation of value function. So we just focus on calculate the value function until it converges. Then we will also have the optimal policy.